So another big picture we'll talk about today, and it is probably the most important lecture on the whole of AC machinery fundamentals. So we have seen how to produce two-pole stator, and now we are going to see how to produce four-pole in the stator, and will summarize up with how to produce 2x pole, the multiple of two poles. Okay, so what's the rule to produce four pole? We're going to see that first. To produce four pole, we need to repeat the three-phase winding setup twice, and since it is a circle, we cannot extend the angle over 360 degrees, so we need to make the angle between the windings half. So that means 60 divided by 2, so 30 it will be. Before it was 60, remember? And so what's going to happen? This was the three-phase winding setup, right? And here is a setup for a four-pole winding, for a four-pole, right? And try to notice that if I bisect it, this whole portion is just this three-phase setup, and this portion is again the repetition of this setup, right? You have a dash, a1 dash, c1, b1 dash, a1, c1 dash, and b1, and again repetition with simply another nomenclature, a2 dash, c2, like that. So the angle between two adjacent windings are cut at half, and that's how we produced four poles. We're gonna see how it produces four pole later on. So the ultimate working rule is that to produce 2x poles, we need x times of three-phase windings, and that obviously means that the angle between two adjacent windings are going to become 60 degree divided by x. Alright. So we'll now see how exactly is a four-pole happening. How is four-pole happening, right? So remember, we are stuck to a nomenclature that we are putting from the prime we are having the current three-phase current coming out, and from the non-prime we are having the three-phase current going in. And in the A section we will have the 0 degree phase, and in the B section 120 degree phase, and in the C section 240 degree phase. Alright, so this is the shape of the three-phase winding. This is IAA dash, this is IBB dash, and this is ICC dash. We're going to consider for some moment of time what's going to happen. Try to see that in this moment P, what's going to happen in this moment P. In this moment P, only IAA dash is positive and rest 2 are negative. Alright, so that means the original direction of the current will hold only for S, but it will not hold for B's and C's. It will get reversed for B's and C's. Right, so that means the originally it was that from primes we get current coming out, that's gonna hold for A. So we'll get current coming out from A1 dash and also from A2 dash, and we'll get current going in to A1 and A2. Sorry, close it will be. And for BB dash is going to be reversed, so that means in the dash section we get current going in, and in the unprimed section we get current coming out, right? Yes, so that's how it is. And in for same for C, in the dash section we get current going in, and in the under section we get current coming out. So if you notice it, that we get three adjacent windings where the currents are coming in or going into the phase. Alright, so we are gonna mark them. Remember, if current is coming like this, the magnetic field direction will be found out from right hand rule. So for these three adjacent windings where the current is coming out, the magnetic field will be like this, going into this direction. For these three windings it will be like this, and for these windings it will be like this, and for these three adjacent going into the phase windings it will be like this. It's just a practice of your for your right hand. Alright, what do you see? We get four positions where either way the magnetic field is coming in or going out fully. So what do we call them? We call them poles, where the magnetic field vector is going in or going out, and where it is entering we call them north pole, right? So this is north pole, and this is another north pole, and where it is leaving is we call that south pole. So this is south pole, this is south pole. So, and here you see that's four pole, that's the four pole we want, that's the four pole we're talking about. So to derive the relation between the electrical frequency and its rotational speed, just like the past video for two pole, we are gonna see what happens to these magnetic poles for another time period, and we're going to consider time period after 180 degree. After 180 degree, the exact opposite situation is going to happen. We're going to call this moment x, and at x IA A dash is going to be negative, IB B dash is going to be positive, and IC C dash is also going to be positive. So that means for A dash the polarities are going to change right now. So the original polarities were primes, we get going out, going in, going out of the base. So that's what that's not going to happen now. To into the primes, a primes, it will go into the base. All right, and on the non-primes it will come out of the base. And for B and C there is going to hold on. So that means for primes it's going to come out of the base. These are the primes, and for non-primes it's going to go into the base. So again we see we get three, what should I say, we should get three adjacent windings having the same sort of direction of currents. So they would produce a magnetic field combinedly. So what will be the direction of for these three windings magnetic field? You just put your thumb in the direction of current flowing, and you see the magnetic field will be in this way. For this it will be like this, and for these windings it will be like this, and for these three windings it will be like this. So where are the north and south poles at this moment of time? The north pole is going to be here and here, because here these two places the magnetic field is entering, and the south pole is going to be here and here. So what can I say? There is a rotation which is anti-clockwise, really. Yes, that's the anti-clockwise rotation we're talking about. This north pole gets here, this north pole comes here, the south pole goes here, and we overall get a rotation of 90 degree, right? These four poles consists of 360 degrees. So the angle between two adjacent poles is 90 degree, and from this scenario to this scenario we see simply the poles gets exchanged from one to other pole, right? So there is 90 degree rotation of poles. So what can you say in common? In common we can say for 180 degree electrical rotation, electrical angle, we get 90 degree, 90 degree magnetic angle. So we get theta SE is equals to twice of theta SM, or in other words theta SM is equals to half of theta SE, and this can be also said as, so this is for 4 pole. This equation we can also say as 4 by 2 theta SM, and this is 4 pole. And what was the 2 pole case? 2 pole case, it was theta AC equals to theta SM, which can be written in another form, theta AC equals to 2 by 2 theta SM. So you see the pole number gets on the numerator. If we try to make a pattern, so we can ultimately say, and it can be proved by mathematical induction, that theta AC is equals to P by 2 theta SM, where P is simply the number of poles that you are producing, and we know how to produce that, right? And if we want to make the equations more distinct, we can say frequency of AC is equals to P by 2 frequency of SM. It has to be, obviously, right? And if AC is equals to P by 2, what is frequency? Frequency is simply the speed. Frequency is simply the speed divided by 60, the speed per minute divided by 60, right? And so what can I come out to be? NSM will be equals to 120 FAC over P, and this is the call for synchronous speed equation, because this is the speed per minute of the motor and it's called synchronous speed. We're going to need this equation throughout our induction motor, and it's the most fundamental equation of whole of this induction motor mechanisms. Alright, and in the closing section of this video, we're going to close the machinery fundamentals right now. In the closing section, I want to talk to you about something a little bit different. It's about reversing the magnetic field rotation direction. We know that we have produced a magnetic field rotation counterclockwise direction before, but how can I produce it to clockwise direction? Or what makes it counterclockwise and what makes it in clockwise? That's what we want to know. I don't want to prove it, your book does a good job on that. I just want to make sure that you get the physics behind it. So what's the working rule? Working rule is that if like polarity windings, that means either way dashes or non-dashes of 0 degree, 120 degree and 240 degree phases are placed clockwise, then the rotation is clockwise, and if they are placed counterclockwise, then rotation is anti-clockwise. That's it. That's the whole rule. Remember, in our cases, we put in A dash the 0 degree, in B dash the 120 degree, and in C dash the 240 0 degree, right? That's the reference we are talking about whole of this section. So you see them, they are placed anti-clockwise. If you want to go from 0 to 120 to 240 degree, you get anti-clockwise. You have to go anti-clockwise, so the rotation of magnetic field will be anti-clockwise. That's the rule. But if you change them, if you simply swap these two, then to go from 0 degree to 120 degree to 240 degree, you need to go clockwise, right? So here the rotation will be clockwise of magnetic field, and here the rotation will be counterclockwise. It can be proved. Your book does a very good job on that, and I will not prove that. Alright, and